Hi, this lecture is about Ethereum and a quick introduction to Ethereum, which is a secure decentralized transaction ledger. Here is the outline of the lecture. First, I'm going to introduce what Ethereum is. Then we're going to see the blockchain paradigm of Ethereum. Then we're going to study Ethereum as a transaction-based state machine. Then I'll explain the proof of work in Ethereum. Although recently Ethereum has switched from proof of work to proof of stake, but I'm going to follow the yellow paper of Ethereum, which explains the proof of work. Then we'll talk about incentivization in Ethereum and the definition of Ether and Wei as the currencies. And then we're going to look at the terminology and definition of many of the terms that are used by Ethereum, and that's going to be a interesting introduction to Ethereum. So Ethereum is a framework that implements the blockchain paradigm in a generalized manner, and it provides the plurality of decentralized resources. Each of these resources has a distinct state and has an operating code, which we call it EVM code, which stands for Ethernet Virtual Machine Code, and I'll talk about it briefly in the next slides. And the resources can interact and exchange messages in a process called message passing that is implemented in the Ethereum ecosystem. And the key goal of Ethereum is to facilitate transactions between parties who have no means to trust one another for different reasons. So that's why they use a decentralized framework called Ethereum. Why they don't trust each other? Maybe because of geographical separations or interfacing difficulties or interfacing incompatibility or incompetence or unwillingness, or because the expense is too much to do the transactions with a third party, or they are uncertain or inconvenient to do it and to do the transactions in the old way, or they are afraid of the corruption of the existing legal systems. So Ethereum in the yellow paper of Ethereum is modeled using a mathematical model called the state machine, which is basically a model that is very commonly used. It has some finite number of states. One of those states are called start state. Normally, state machines are drawn using a graph shape diagram. Then the states are represented by nodes, and there are directed edges or directed arrows between the states. We call those state transitions or state changes. Each state machine defines rules for state transition or state changes. And given this introduction about the state machines, we can say Ethereum can be viewed as a transaction-based state machine. Why do we call it transaction-based? Because you need to execute a number of transactions to go from one state to the other. We start with the genesis state, that's the start state, and incrementally execute transactions to change the genesis state eventually to some final states. And let's take a look at this diagram so I can explain Ethereum a little bit easier. So there's a first block of transactions. Let's call that the genesis block. And as we go forward and we change states, we create different blocks of transactions, and these black blocks that you see are gonna make a chain of blocks that will be trusted by all. And as you see, that black that the path of black blocks is not the only path. There are multiple paths which are generated because of fork. When do we say a fork is generated? When from one block you have two exiting arrows to two different blocks. Usually the existence of forks is not pleasant, and we typically want to avoid forks because they disrupt the system and force people to choose which chain they believe in. So it's going to create some difficulty for users of the network to basically reach to consensus, because Ethereum relies on the longest chain consensus. Now, in the existence of different paths, the question is, how do we determine which path is the most valid and prevents multiple chains? Ethereum uses a mechanism called Ghost Protocol, which stands for Greedy Heaviest Observed Subtree. And if you want to simplify the Ghost Protocol, you can say Ghost Protocol says we must pick the path that has had the most computation in it. That's basically the most reliable because it has the most computational power spent on it for its creation. And one way to determine that path is the longest path is to use the block number of the most recent block, which is the leaf block, and that number basically represent the total number of blocks that are in that path with exclusion of the genesis block. So for example, the block number on this block is 1, 2, 3, 4, 5, 6, 7, 8. And the block number of this one is basically 1, 2, 3, 4, 5, 6, 7. So because this is 8 and this is 7, we assume that we conclude that this is the canonical blockchain because we have spent the most computational power on it as a whole, as the whole society of Ethereum. And as I said, the higher the block number is, the longer the path is, the greater the mining effort that must have gone into arriving to that leaf. So let's talk about the relationship between a block and a sequence of transactions. Basically, a block is created to collect a number of transactions and put them together in the form of a block with some header. Blocks are chained together using a cryptographic hash as a means of reference, and you can think of a block like a journal that records a series of transactions, and it also keeps the previous block and the identifier of the final state in it. A block doesn't really keep the whole final state because it takes a lot of space. Instead, it only stores the ID of that final state. The blocks have to be constructed and created by miners in order, which are basically nodes in the network, so that we can make progress in the blockchain. But the miners need to have some incentives to create new blocks, and that's very similar to the mining process of Bitcoins. So miners would like to have some incentives. The incentivization takes place as a state transition function, which adds value to a nominated miner, or to the nominated account of the miner. Now that you're familiar with the concept of states and transactions and blocks in Ethereum, let's take a closer look at state transition functions um, that basically regulates the transition and state change in the Ethereum state machine. Each state in Ethereum includes information such as, let's say, account balances, reputations, trust arrangements, data related to information to physical world, and to summarize it, you can say any information that can be digitized and stored by a computer. Transactions which are packed into a block represent a valid arc or a valid edge or a valid transition between two states. Why do we call a block of transactions a valid arc? Why do we say valid? Because there are far more invalid state transitions and state changes than valid ones. And there exists a way to distinguish valid transitions or valid arcs from invalid arcs. Invalid state transitions are something like, let's say you want to reduce the balance of an account without an equal and opposite increase in other account. So that's obviously an illegal action, so it doesn't have a valid state transition in the Ethereum as a state machine. If I want to go to a little bit more details of a state transition, we can say this. Let's say you're in a state 1, and the state 1 is the state of time t, which is represented this way, sigma t. These notations and these symbols are all taken from the yellow paper of Ethereum, which is the main source of Ethereum. And we're going to have a transition from sigma t to sigma t plus 1, right? Sigma t plus 1 is basically a state 2. And in order to do this transition, we use a sequence of transactions collected in a block called B, right? So this is block B, which is defined this way. It's basically a sequence of transitions like T0, T1, T2, all the way to, let's say, Tn minus 1, right? So how do we do this transition? There exists a transition function, which is this one. It's called the capital upsilon. That's a Greek alphabet symbol. And this function basically gets one state like sigma and one transition, and it returns the next state. So using upsilon, using the state transition function of Ethereum, we're going to change sigma t to, let's say, sigma t1, where 1 is the superscript. Then that transition happened using transaction t0. Then we apply transaction t1 and we create sigma t2. Then we're going to apply transaction t2 on sigma t2, and using the transition function upsilon, we're going to create the next state or the next substate, sigma t3. And when you apply all of them all the way to the last transaction, which is Tn minus 1, you will create, or you will changed to this state. Sigma t, the subscript is t, and the superscript is n, and that's basically equal to sigma t plus 1, which is basically the next state, right? So in order to transition from state 1 to state 2, we're going to use all of the transactions that are stored in this block. So let's talk about a very important part of Ethereum, which is the mining process, which allows you to create new blocks and make progress in the network. Mining, by the definition that is provided in the yellow paper, is the process of dedicating effort or working to bolster one series of transactions in the form of a block over any other potential competitor block. And it is achieved using a cryptographically secure proof, and the scheme is known as proof of work. Now, you all know Bitcoin and the Bitcoin's proof of work. Ethereum has recently switched from proof of work to proof of stake, but because this lecture is based on the yellow paper, I'm going to keep talking about proof of work. But just for your information, Ethereum switched from proof of work to proof of stake on September 15 of this year at 142 Eastern time. And the last Ethereum block finalized on their proof of work was this number. So as you see, we had about 15.5 millions of blocks basically finalized on their proof of work. But after that, Ethereum has switched to a more environmentally friendly and, let's say, greener way called proof of stake for mining. Now, let's compare the proof of work of blockchain with Ethereum, and let's talk about that. One plague of the Bitcoin world and the mining process of Bitcoin is the application-specific ICs, application-specific integrated circuits. They are, what is ASIC? The ASICs are specialized pieces of computer hardware that exist only to do one single task. For Bitcoin, to basically do SHA-256 hash function, to basically calculate SHA-256 hash function. So while ASICs exist for a proof of work function, like the proof of work of Bitcoin, the fairness of mining is in jeopardy. Why? Because not all miners have access to ASICs, and maybe someone can make a lot of profit because of the existence of ASICs, and because it has access to a lot of ASICs. Now, because of this, Ethereum has decided to come up with a proof of work that is ASICs resistant. What does that mean? That means it is either too difficult or economically inefficient to implement the proof of work function using a specialized computer hardware, the way the SHA-256 hash function can be implemented using an ASIC. An ASIC resistant should try to avoid that. So let's talk about how we can make a proof of work function ASIC resistant. There are two main directions. One is to make the proof of work function sequentially memory hard. What does that mean? That means to design the function so that determination of a nonce requires a lot of memory and bandwidth, so that the memory cannot be used in parallel to discover multiple nonces simultaneously, and that basically creates a barrier for doing proof of work mining in a very small period of time. And the second way of creating an ASIC resistant proof of work is to make the type of computation in the proof of work function in a way that it requires a general purpose hardware, and it cannot be executed on a application specific IC or integrated circuit. For Ethereum 1.0, the designers have chosen the first path. That means to make the proof of work function sequential memory hard. And I'm going to briefly explain how the proof of work in Ethereum looks like. This is how it looks like. Basically, proof of work is a function that is applied on three parameters. The first parameter is a new blocks header without the nonce. The second one is the nonce of the new blocks header. And the third one, which is D here, is basically a large data set needed to compute the mix hash. And HD, the number that you see here, is the new block's difficulty level. As you may remember, in blockchain, we could have adjust the difficulty of the mining process. Same story as Ethereum. You can adjust the difficulty because, you know, over time, the computational the technology of computers will change, and we have the exponentially growth rate in computer technology. So we need to have a way to adjust the difficulty level of mining. So that's why we have HD here. The higher this HD is, the lower this quotient will be. And N, which is the nonce that has to be a positive number, will have a tighter limit. And therefore, in order to find N, you need to spend more time. And in order to understand POW, you can take a look at the yellow paper. I'm going to briefly explain it, but basically, ETH hash is the planned proof of work algorithm for Ethereum 1.0. Again, I don't want to go through the details of ETH hash, but you can take a look at how, you know, that algorithm works and how, you know, the proof of work is calculated. This is basically equal to an ordered pair. The first one is the first element in that ordered pair is this, and the second one is going to be this one, where, you know, KEC is basically the third generation SHA, is SHA-3. It's kind of similar to the SHA-2, the SHA-256 that you know, but this is like the upgraded version, which was proposed, I guess, in 2015, and it's accepted by NIST. And you can check out all the details. I don't want to go through the details, but this is the slide that tells you that the proof of work function is not as simple as the proof of work of Bitcoin. The main reason is so that we can have an ASIC resistance for this function. You can check out the details. I don't want to go through it, but it's out there. It's in the yellow paper. If you want to read the details, you can check out the yellow paper. Next, let's talk about some definitions regarding incentivizing computation in Ethereum. In order to incentivize computation within the network, we need to have a mechanism for transmitting value, and the basics of that mechanism relies on having a currency so you can transmit value. Ethereum has an intrinsic currency called Ether. which is sometimes referred to as ETH, or it is represented by this symbol, which is a capital letter in Greek alphabet. It's Psi, and the smallest subdenomination of Ether um, is called Wei. So remember, in Bitcoin, it was Satoshi, but here we call it Wei. And 1 Ether is defined as 1 exa Wei, or 10 to the power of 18 Wei. And there are some other subdenomination of Ether other than Wei, which is basically used for specifying the transmission, specifying the values in Ethernet network using a whole number, using an integer. Other than Wei, we have, other subdenominations like Sesabo, which is 1/1,000,000 Ether. That means 1 Ether is equal to 1 mega Sesabo, or 1 Ether is equal to 10 to the power of 3, or 1,000, or a kilo Fini. And these are the subdenominations of Ether, which is a currency in Ethereum. Finally, I'm going to introduce some of the terminology in Ethereum that they're all defined in Ethereum's yellow paper. I have extracted these definitions because these are very important for you to understand how Ethereum works, and it's very useful for the later discussion on Ethereum. Basically, here is the list. The first one is external actor, which is a person or other entity able to interface to an Ethereum node, but external to the world of Ethereum. So that's an external actor. It can interact with Ethereum through depositing signed transactions and inspecting the blockchain and associated state. An external actor must have one or more intrinsic accounts. The second term is address, which is a 160-bit code used for identifying accounts. Each account must have a unique address. The next one is world state, which is, or simply a state, which is a mapping between addresses, which are those 160 identifiers, and account states. What is account state? Account state is a 4-tuple made of 4 fields: a nonce, which is the number of transactions sent; a balance, which basically the number of ways owned by the address, by the account; and storage root, which is a 256-bit hash of the root node of a Merkle-Patricia tree. You can check out the Merkle-Patricia tree details in the yellow paper. We talked about Merkle tree before, but this is a special one. And then code hash, which is a hash of Ethereum virtual machine code that for an account that should be executed once the account holder, once the address of the account holder receives a message call. Next, we define account. Accounts have an intrinsic balance and transaction count maintained as part of the Ethereum state. Each account has a single address that identifies it. The accounts also have some EVM code and possibly empty or non-empty storage state associated with them. The next thing I'm going to define is basically transactions, which is pieces of data signed by an external actor. They represent either messages or new autonomous object, which I define later. Transactions are recorded into each block of the blockchain. Next, we define autonomous object, which is a notional object existent only within the hypothetical state of the Ethereum. It has an intrinsic address, and therefore it has an associated account. The account will have non-empty associated EVM code, which basically is a code that will be executed on a Ethereum virtual machine, incorporated only as a storage state of that account. A storage state of an account is basically the information particular to the account that is maintained between the times that the account's associated EVM code runs. Message is defined as a data, which is a set of bytes, and values specified as ether, that is passed between two accounts, either through the deterministic operation of an autonomous object or the cryptographically secure signature of the transaction. And the message call is the act of passing a message from one account to the other. Then we define gas, the fundamental network cost unit, which is equivalent to the Bitcoin transaction fee. The gas is paid for exclusively by Ether. You cannot use any other currencies. Gas doesn't exist outside of the internal Ethereum computation engine, and its price set by the transaction, as I said before. And miners are free to ignore transactions whose gas price is too low, just like Bitcoin miners that ignore transactions with very low transaction fee. They may not ignore it, but it takes a lot of time to be processed. And the next term is contract, which is an informal term used to mean both a piece of EVM code that may be associated with an account or an autonomous object. We talked about smart contracts before, and object is the same, is an alternative word for autonomous object. Next, we define app, which is an end user visible application hosted in Ethereum browser. What is Ethereum browser? Or sometimes they call it Ethereum reference client. It's a cross-platform GUI of an interface similar to a simplified browser like Chrome that is able to host sandbox applications whose backend is purely on Ethereum protocol. And the next one is Ethereum virtual machine, or short we call it EVM. It's a virtual machine just like Java virtual machine or CLR from Microsoft, which is the common language runtime, that forms the key part of the execution model of an account's associated EVM code. So each account has EVM code, so that code is executed in the EVM environment. Ethereum runtime environment, or ERE, is the environment that is provided to an autonomous object executing in the EVM. And EVM code is basically the bytecode that the EVM can natively execute, just like the Java bytecode that JVM can execute, or the intermediate language bytecode that CLR can execute for .NET languages. EVM code is used to formally specify the meaning of a message to an account, and EVM assembly is a human readable form of the EVM code. And here is my only reference, the yellow paper of Ethereum written by Gavin Wood in 2014.